Yeah, so I'm going to tell you today about some recent work that we've done on clean graphene heterostructures. So this talk, I'm not sure, this is a very broad audience, and yet at the same time has many world experts in these types of fields. So I've done my best to kind of split that difference, but just interrupt me if things are unclear in the middle. I'd be happy to take your questions on the fly. So, so the topic of today's talk is what happens in systems, two-dimensional electron systems exposed to large magnetic fields and periodic potentials, essentially when you can really reduce the disorder to the point where interaction effects become important. So I'm going to tell you a bit about the general structure of Chern bands in the Hofstadter butterfly, which is sort of the non-interacting model from which one begins to analyze these types of systems. I'll tell you about the specific physical systems and the specific observables that we like to measure, and then I'll walk you through a data set of what happens when you realize a system with a strong lattice potential and a strong, and a strong magnetic field, and then sort of tell you some of the reasons to be excited about this. Let's see, where can I stand that will, maybe this is okay. So the basic physics that, the basic physical problem that we're going to study is that of a Bloch electron in a magnetic field. So everybody knows the solution to a two-dimensional electron exposed to a large magnetic field in the absence of a periodic potential is described by the Landau levels. These are very flat bands. Semi-classically, you can think about them as many different positions in a two-dimensional sample with electrons undergoing quantized cyclotron motion and characterized by this length scale that's the magnetic length, which is about 25 nanometers at a Tesla and then goes down like square root b above that. In the absence of a magnetic field, but in the presence of a periodic potential, it's another standard textbook problem of Bloch waves, right? So the relevant length scale for Bloch waves is, of course, the lattice constant. And it turns out that if you consider both of these things at the same time, that quantum mechanics problem is also exactly solvable, but it has a pretty pathological solution. You find that you can solve the combined effect of these two you can solve it exactly for any rational relationship between the magnetic flux and the area of the unit cell. So for rational values of flux per unit cell, you find the exact solution. And strangely, it has Q eigenvalues, where P over Q is the rational value of the flux. And that's pretty strange because it means as a function of a continuous parameter, like the lattice constant, or more physical for us, the magnetic field, you have an extremely discontinuous single particle energy spectrum. This was first noticed by Osbel, but then of course famously solved on a computer by Douglas Hofstadter, and the result is this beautiful Hofstadter butterfly spectrum. So what's plotted here in white are the eigenvalues of this problem. This is for a square lattice. I'll discuss later that we actually end up doing it on a triangular lattice. Is not quite the classic one, but the basic structure remains the same, that as a function of magnetic field, really flux per unit cell, you have this very discontinuous eigenvalue spectrum that nevertheless has certain structure to it. In particular, although the eigenvalues are always discontinuous, the gaps between them are certainly continuous. They're well-defined regions that have no eigenvalues as a function of magnetic field. And then you have these bands, which are themselves composed of mini-bands, composed of mini-bands, composed of mini-bands. So this has a sort of self-similar fractal structure. Yes?
Can you explain on here where that quantized number of eigenvalues are, if I'm in a particular
value? Pick a magnetic field, and then take a cut here. You're going to see, if you zoom in, you'll see that there's Q.
Does the fractal structure mean that there's an infinite number of things along any cut, if I look close enough?
Well, no, that's not right. So there's Q. Yeah, so let's see. Let me remember. I
think it's transposed.
Is it transposed? It might be trans. It doesn't matter. Sorry.
I don't think that affects the answer.
Yeah. I don't think it's transposed. But yeah. So basically, you have what you really have are Q. Let's see. You have Q bands, right, for a given rational value of the flux, right, and then within each band you have a sort of distinct set. You end up with lots of them for when, let's say you're at 99 hundredths of the flux, then you're going to have 100 different bands. But then they sort of get wider. Yeah.
Q, what he's asking is correct. If you take a random Q, it's going to be irrational.
Yeah.
Then it will be fractal.
Sure. Yeah. That's right.
Values of
yeah.
Q, It's not.
Oh, so there's, I'm only allowed to take specific cuts in order for
No,
this
you
to
can't
be-
take any cut.
Yeah, but
For the P over Q
Right,
is what
exactly.
yeah, so these are always calculated for rational P over Q.
Are those
Yeah.
the values where you go through like what looks sort of like vertices, kind of?
Yes, exactly, right? These things tend to meet at some large rational, large denominator rational approximate. Yeah. Okay, so, right, so okay, maybe if there's one sort of take-home message of the point of this talk, it's that actually this fractal nature of this spectrum turns out not to be relevant for experiments. And the reason, and in fact, it's not even the reason why this band structure attracted the type of interest that it has attracted over the last 30 years. The real reason for that is that the sort of special thing that characterizes these bands and mini-bands is rather a topological property, which is their Chern number. Okay, so it was shown by Thales and collaborators, of course, famously, that if you have some band, then it's going to be characterized by a quantized Chern number, and that quantized Chern number is related to the Hall conductivity. And so you can just take your band wave function. You can do this for the Hofstadter spectrum at some given magnetic field. You can take each of those bands. You can calculate these Chern numbers, and you'll find that generically in the Hofstadter band structure, all of the bands have Chern numbers that are not equal to 0, or anyway, many of them have Chern numbers that are not equal to 0. And what that means physically is that if you take that Hofstadter band structure and think about it as a phase diagram for non-interacting electrons, and imagine going to some physical magnetic field and then filling some number of bands. Let's say you put your Fermi level inside one of these gaps, then you can calculate the Hall conductivity by simply summing over the Chern number of all those occupied bands, and generically that's not going to be equal to 0. So you're going to have a quantized Hall effect, in fact, this is sort of was the original view of the topological nature of the quantum Hall effect comes effectively from this paper, of the integer quantum Hall effect. It turns out that this is more generic than just the Hofstadter butterfly, right? All kinds of systems with lattices and broken time reversal invariants can give you similar Chern band physics. The Haldane model of the honeycomb lattice with staggered flux is a good example. These types of systems generically tend to be of interest to a number of cold atom people because they give you a way of maybe making an integer quantum Hall effect without actually needing a large net magnetic field. Yeah?
Just a historical comment. I'm sure you know, because I was already active. David Thales actually didn't know the word Chern number. That came in.
Yes, sure. That came later. But they did calculate it, right? Yeah.
Barry Simon pointed out
Yeah. You're really calculating this thing. Yeah.
Chern's work was not even known in math. This paper really made that.
Yeah. No,
It's kind of interesting how a subject goes. He rediscovered Chern number in this paper actually.
Okay, so if we take that idea and then try to interpret this as a phase diagram for non-interacting electrons, we can color code it basically based on the Hall conductivity. And you can see this in this diagram where, let's say, red, orange, blue, etc., all indicate different integer quantized Hall effects, right? And you can imagine, again, just taking electrons, filling this band structure so that you've filled some integer number of bands and mini-bands, and you'll get some quantized Hall effect. But of course, that's true for at any level of the fractal hierarchy. You can zoom in, and between any eigenvalues, you can always find some gap. It might be arbitrarily small, but you can find some small gap here. And you can see that the Hall conductivity is a function here of energy, but it would really be as a function of electron density. If you're imagining filling this band structure, you're going to change Hall conductivity in some kind of complicated way where it's not just monotonic. So the classic case of the integer quantum Hall effect, of course, happens in Landau levels, right? And in this diagram, actually, Landau levels correspond to the very small magnetic field limit. And that makes sense. In a normal crystal, you have a crystal lattice constant. It might be a couple of angstroms. You have the magnetic length, which might be tens of nanometers. So your magnetic flux per unit cell is typically extremely small. And you're down in this limit where you can see that each of these lines basically becomes arbitrarily narrow, and they all converge. And this is the Landau level limit. Each of them has a Chern number of 1. The non-trivial, non-unity Chern numbers only start to happen when you get to large flux per unit cell. And so experimentally, that was essentially the challenging fact. If you want to study the details of this spectrum, you need to get to very large magnetic fields per unit cell. That's basically not possible to do in normal crystals because of few angstroms versus tens of nanometers. You need magnetic fields of tens of thousands of Tesla. It's not really plausible. So before I tell you how we do that, I want to sort of point out some features of Landau levels that are not topological but that are important. So they are Chern bands, right? So they give you the integer quantum Hall effect. They have this feature that's generic to the Hofstadter butterfly spectrum, but they also have the really compelling feature that they're very flat bands, right? And so if you have a very flat band, in a Landau level, the bandwidth is essentially just a function of disorder in your system, right? If you don't have a lattice, there's no intrinsic bandwidth to a Landau level. And it's just a function of the disorder. And that means that even though your Coulomb interactions in a typical 2D electron gas are comparatively weak, right? It's just, inter-electron spacings might be tens of nanometers. These are not strong interactions in the sense of a system with very high electron density. These are systems with low electron density. Nevertheless, it can be the dominant energy scale in your system, because if you can make a system clean, you can make the bandwidth here, gamma, very small, and therefore you can make Coulomb interactions dominate. So if you ask the question of what happens at partial filling of a Landau level, you're basically asking the question of how do I minimize Coulomb repulsions, because all of the single particle states are effectively degenerate, at least certainly compared to the Coulomb interaction. So you basically can construct ground states to minimize this repulsion energy, and that's basically the bare many-body problem. It's a hard problem, and it has a lot of interesting solutions. So among those solutions are kind of two general classes. There are solutions based on symmetry breaking. So for example, in multi-component systems, when you have a spin degree of freedom, you will get types of quantum Hall ferromagnetism, which are very sort of perfect ferromagnets. You can get very deep into the exchange-dominated regime, and there's skyrmion physics and all kinds of things like that. You can crystallize electrons, right, and form Wigner crystals and other types of electron solids and pneumatics, other types of symmetry breaking that can happen. And then sort of the second class, which is somewhat more specific to Landau levels, is that of topological order. So in particular, you can get fractional quantum Hall states, which are probably the most famous example of an answer to the question of how do you optimize Coulomb interactions within a Landau level. It's what happens if you have some rational filling of the Landau level. You'll form a set of abelian fractional quantum Hall states of various kinds, both the original Laughlin states and their relatives, various multi-component states, as well as non-abelian fractional quantum Hall states. There's sort of a whole zoo, many experts in this room on all of that. The thing that I want to point out is that, of course, none of this physics is theoretically unique to Landau levels. Landau levels have just been a convenient experimental arena in which to investigate it. Symmetry breaking is certainly not unique to Landau levels in the sense that there are many types of systems that show symmetry breaking. We've organized condensed matter physics along symmetry breaking for many decades as far as our understanding of all kinds of systems, superconductors, crystals, all kinds of things. Topological order, in contrast, is relatively rare experimentally. It's hard to find good examples of topological order. Maybe gap spin liquids, but basically fractional quantum Hall systems in Landau levels have kind of been the only game in town for understanding interaction-driven topological ordered physics. And what I'm going to tell you about in this talk is how you can generalize not only symmetry breaking physics, but also topological order to a system that is related to Landau levels, but not exactly. In other words, can you get a fractional quantum Hall inside a Chern band within the Hofstadter butterfly that's not exactly a Landau level? Okay, so the measurement that we make, so we study graphene and graphene heterostructures. The measurements that we make are a little bit unconventional, hardly novel, but they're not the usual. We tend to measure capacitance for reasons that I'll tell you about later. So in a two-dimensional electron system, if you have, let's say, this graphene sheet, and then you have a top gate and a bottom gate so that you have separate electrical access to each of these plates of this three-plate capacitor, you can measure the differential capacitance between, say, the top gate and the graphene, or the bottom gate and the graphene, or indeed the bottom gate and the top gate. That's these three quantities. This is what I'm calling the top gate capacitance, bottom gate capacitance, and penetration field capacitance. And as a function of the geometric capacitance between these two and the density of states of the graphene, you'll find that, in fact, you can derive these formula which tell you that when you measure the top gate capacitance, for example, you are sensitive to this density of states. And the reason for that is relatively simple. Capacitance is basically measuring the energy cost of moving charge around a system. Moving charge around a system costs you the electrostatic energy of putting an electric field inside your dielectric material, but it also costs you the energy of changing the Fermi level in your two-dimensional electron system. And that cost of changing the Fermi level is just the density of states. So you're ultimately sensitive to density of states. And all of these different quantities basically probe the same type of thing. We're going to turn out to like to measure this one for various technical reasons.
But
yeah.
When you're measuring, if you could just go back a moment. So when you're measuring capacitance of each of these various layers. What are you, I always think of a capacitor as being a two-terminal device. So
Right.
that's
The other one is grounded.
Grounded.
Yes, yes. So that's important. So let's
So where is ground?
ground. Let's say so in the measurements I'm going to show you, ground is the graphene.
Okay.
Okay, which means that the graphene is at 0 electrochemical potential, right? So its electrical potential can move as long as its chemical potential moves the other way. And you can think about this measurement pretty simply in the two limits. So if you imagine putting an AC voltage on the bottom gate and measuring the charge induced on the top gate, if the graphene is a perfect metal, it will simply screen that charge. If the graphene is a perfect insulator, it won't screen that charge at all. And that's what maps 0 to infinite density of states to the interval basically 0 to 1 in these units. Or 0 to 1 over 2, to C over 2. Okay, so the physical systems that we study are kind of graphene plus, and specifically they're graphene heterostructures made out of two different types of materials, graphene and graphite, and hexagonal boron nitride. So the basic innovation that we've achieved recently is understanding what the main source of disorder is in graphene devices in general over the last 10 or 15 years. So basically, we started, to give a brief history of this field, graphene started with graphene devices on silicon oxide. It turns out that they were relatively clean for something that you make with Scotch tape and sort of very elementary e-beam lithography practices, but that the basic mechanism that limits ultimately the bandwidth of your Landau levels, but also all kinds of transport properties, is the fact that silicon oxide is an amorphous material. It has lots of charge traps, and this was sort of the leading problem. You got mobilities on the order of 10 or 20,000 at best if you were very careful in that type of geometry. Fast forwarding, sort of in keeping on the direction that we ended up in, if you can remove that silicon oxide substrate and replace it with something that doesn't have the same density of charge traps, then you can improve on that. So hexagonal boron nitride was kind of the solution to that. Hexagonal boron nitride has the same crystal structure as graphene, but it's an insulator because boron and nitrogen have very different energies. So it's 4 or 5 electron volt energy gaps. It's atomically flat. You can get large single crystals, and you can make structures that have graphene sitting on hexagonal boron nitride. And that had a major improvement in the quality of both zero field transport properties as well as high magnetic field properties. Whether you can see fractional quantum Hall states, for example, whether you can see that in fact the degeneracy lifting within a Landau level is arising from interactions rather than from disorder. More recently, we were trying to understand what still limited it. And it turns out that I think in every field of physics, one eventually learns that metals are not equipotentials, despite what were taught previously, right? And that was true here also. So we typically fabricated these devices with gates that were made of metal. So we would put a metal gate here in order to change the charge carrier density of the graphene. But it turns out when you deposit a metal in an evaporator, it comes down in little different grains. Different grains have different facets. Different facets have different work functions. And different work functions basically are little patches of potential. And so this patch effect, of course, once you know what it is, it's very easy to find lots of literature about the patch effect and every kind of thing. But that what was limiting. That essentially made a long wavelength kind of disorder potential for the graphene. Luckily, the way we assemble these, it's relatively easy to replace some patch effect riddled metal film with a single crystal and a single crystal facet in the form of graphite. So what we did was start to build devices where essentially everything, the gates, the dielectrics, the channel itself, and the contacts are all made of single crystal van der Waals materials. So you can make a device that has hexagonal boron nitride gate dielectrics, a monolayer or bilayer graphene contacted by graphite and gated essentially also by graphite, so that the charge density throughout the graphene sheet is highly uniform because all it sees is single crystals, planar single crystals that don't have any dangling bonds. They don't have any kind of intrinsic disorder. And so the result you can see here. This is basically one of these penetration field capacitance measurements. Yes. Yeah.
So how much did lifting of magnetic field, just from material science viewpoint, how much did the minimum conductivity change and the puddle effect go away? How low can you go in density doing this?
That is a good question. It is slightly more complicated than I can answer.
Is it understood?
So the observation that we have made, it is not the same observation that is made in every other group, is that almost all of our graphene devices made in this way have a large energy gap at zero magnetic field.
Interesting.
Okay? There's a single particle mechanism for that, which is just AB sublattice symmetry breaking. but statistically, it's like almost all of them, right?
What are you thinking about?
We're thinking
What
about
is the gap size? What do you
10, 20, 30 MeV.
That large?
Yeah. It depends. It depends,
But
right?
more than an MEV typically.
Oh yeah. It's we like the 1 MeV devices because that turns out to be like quite useful for certain things. But this device here is a monolayer graphene. I'll digress for just a second and answer your question of why that's an interesting question. This is a monolayer graphene device. It has a large energy gap, about 30 millivolts that we measure at 0 magnetic field. Very well developed fractional quantum Hall starting from about a Tesla. And due to this energy gap in part, there's also even denominator fractional quantum Hall physics that appears in monolayer graphene. Do we think to some phase transition that's ultimately related to the size of this energy gap? Lots of knobs to turn. Some of them we understand, some of them we don't. From a material science point of view, we don't really understand.
You have some of the advantage of gallium arsenide with the gap in graphene.
A lot, yes. You can certainly realize that limit. Yeah.
So just to clarify, the single particle origin just would be from a mismatch. The EV potential would come from the boron nitride?
Correct, yeah. Why it ends up being so big, I mean, there's a moire potential also.
The AB symmetry is broken.
But it's basically broken. So then you're arguing about price in some way, right? How much is it? How much?
You're surprised because you don't expect the graphene to be lattice matched with the boron. I mean,
It's certainly not lattice matched. It may be locally lattice matched, and there are then domains that oscillate on the order of 50 lattice constants. But then when you sort of coarse grain that out, and you end up with sort of the largest possible gap that you might have had any reason to expect, even if it were fully lattice matched, that's a little bit surprising. I mean, I would say not fully understood.
So does the lattice mismatch lead to another regular structure?
Indeed it does, and that is the subject of today's talk, which I'm taking my sweet time getting around to, right? So I have one more slide, and then we'll be there, okay? So let me first just finish describing this data, because this is the type of data that we're going to see a lot in this talk. This is a function of charge density, so you're applying voltages to these gates, and as a function of magnetic field. And all of these lines, all of these dark lines are energy gaps. That's where the capacitance, this penetration field capacitance, is going up because the system is becoming incompressible and insulating, and each of these is a gap. So these are integer quantum Hall gaps, and then all of these little lines are fractional quantum Hall gaps, and it's hard for us to know what our mobility is. So if we want to compare to gallium arsenide, for those who are familiar with the gallium arsenide literature, the way you measure mobility in gallium arsenide is you take a centimeter size chunk of wafer, you measure the Hall effect, you measure longitudinal resistivity, you divide one by the other, and that gives you the Hall mobility, basically. The problem is that even before we made this innovation, the mean free path, we can only make these devices so big, maybe 10 by 10 microns. The mean free path was already bigger than the size of the device. So you don't get much out of zero field measurements. Basically, the only kind of metric of quality that we have is fractional quantum Hall, and that depends on a lot of things, including really understanding the many-body physics. So we don't really know. We certainly know it's a lot better than it was before, but if you compare sort of comparable measurements in gallium arsenide, we're in the tens of millions sort of mobility range in appropriate units. Okay, so indeed, so there's a lot of fractional quantum Hall physics one can do that in many,
What are the sizes? I'm interested in the
distances? Yeah, so we try to make this relatively thick so that we don't screen any interactions. That means for us something like 40 or 50 nanometers. Thickness of the hexagonal boron nitride, sometimes a little bit more. Yeah. Certainly, if you start to make them thinner, you start to see changes. We don't understand it quantitatively, and we haven't done it systematically. So besides the sort of fractional quantum Hall physics I showed you, the kind of real trick that you can play in these van der Waals heterostructures that's really different from what you can do in conventional 2D materials leverages the fact that you are starting from more or less stable two-dimensional crystals, and you're putting one on top of the other. So you're not restricted to what a kind of relatively stable or metastable growth window might permit you to grow, for example, in an MBE system. So you take a graphene and you take a hexagonal boron nitride, and actually during the assembly process, you have control over how you put one on top of the other. So you can control this angle between the two relatively carefully. It's somewhat approximate, but at the same time, it's pretty easy to make these samples, so you can make lots of them, and it's relatively easy to know what the ultimate twist angle is. And in particular, if you say, take graphene and align it rotationally to boron nitride, that intrinsic lattice mismatch of a couple of % gives you some long wavelength period. I don't know if it sort of resolves from your angle, right? But you can see that there's some much larger than lattice constant. This is exaggerated. In fact, it's actually more on the order of 50 lattice constants. Moiré pattern, this is the same pattern that goes into Moiré silk, which mostly went out of fashion 100 years ago, but is still de rigueur in clerical headgear, I discovered from a Google search. So anyway, this is sort of just a simple beating of these two mismatched lattices. And you can see that, if you take an STM micrograph of graphene on hexagonal boron nitride, these were sort of a set of different devices. The way we were making devices at this time, there were wrinkles, and so between different wrinkles, you'd have different lattice orientations, and you can see that you have Moiré wavelengths on the order of 8 nanometers, 4 nanometers, 3 nanometers, 12 nanometers, depending on exactly what the rotational angle between graphene and boron nitride is. Subsequent work, actually, I would point out, these are extremely regular periods, right? To some degree, it seems like the irregularities here are actually caused by the scanning tunneling tip more than they are by anything intrinsic, that the interaction, because these are all van der Waals interactions between, say, graphene and boron nitride, the interaction of the graphene with this local tip potential is just as strong, so there have been some nice works where they kind of push these around a little bit. It's actually hard to measure them without, non-invasively. But for the purposes of today's talk, what matters is that if you push this to sort of the larger end, you end up with Moiré wavelengths on the order of 10 nanometers. And on the order of 10 nanometers means that you have a flux per unit cell on the order of 20 Tesla, and 20 Tesla is a magnetic field that is relatively accessible for experiments. So, yeah.
Is this something you can control, or this is just sort of an accident of where the domains end up?
Now we can control it reasonably well. This work is a little bit old at this point, but you can sort of more or less line up edges, and it turns out that if you line up a graphene edge, you line up a boron nitride edge, you have a reasonable chance of nailing them to close to 0 degrees, and then they want to be at 0 degrees. That's actually an energy minimum as a function of this rotation. So you can kind of.
So you make the two separately and bring them together. It's not just sort of. The graphene is not deposited on.
We deposit it by hand. We pick up a sheet of graphene, we have a sheet of boron nitride, and we put it on top, one on the other. We don't know the lattice orientations exactly beforehand. We know them maybe modulo 30 degrees. But then if you just heat the whole thing, if you're off by a couple of degrees, it'll tend to want to align, because that's just structurally lower energy. Okay, so the topic of this talk is basically what happens in the same regime of high magnetic fields when you have a superlattice like this. So just to give a comparison, the data I showed you before was for a monolayer graphene with no superlattice, right? And the main feature that I want you to notice is that all of these lines, each of which indicate an energy gap, extrapolate to a point, it's not on this graph unfortunately, of 0 electron density and 0 magnetic field. And that's basically the property of Landau levels. This is electron density. The degeneracy of a Landau level simply scales with field. So these Landau fans always extrapolate to 0 magnetic field and 0 density if you just have a one-band system. When you have a superlattice, it's much more complicated. One thing is the same, which is all of these dark lines still follow linear trajectories within the space of electron density and magnetic field, but not all of them extrapolate to 0, 0. Okay, and that, as it turns out, is going to be a consequence of the lattice. So in this particular device, the one that I'm going to show you data from today, half a flux quantum per unit cell is happening right around 24 Tesla, right in here. So we're right in the regime of the Hofstadter butterfly, where you expect the rich physics to happen, where all of these Hofstadter bands now have lots of internal structure, and we can access that. Okay, so following Hofstadter's work, Vannier actually figured out that for that non-interacting model, you don't get the same rich physics of the Hofstadter butterfly, all of these beautiful pictures, if what you're actually doing is just varying the charge density and the magnetic field. All of those beautiful mini bands and so on just collapse onto lines in the plane that we're actually measuring, which is magnetic field and charge density. And that has to do with the fact that the degeneracy of those bands is changing all the time as a function of magnetic field. And basically what he found was that if you then calculate what happens along these gapped trajectories, they all have to follow lines within this plane that are characterized by two quantum numbers. One of them is the slope, and one of them is the intercept. And for the non-interacting Hofstadter problem, basically all of these t's and s's have to be integer valued. Okay, that basically gives you the full spectrum of what you can observe if you have non-interacting physics of an electron in 2 dimensions in a magnetic field and a periodic potential. You have these linear trajectories for the gaps, so all of the dark lines in our data, and they're all characterized by these quantum numbers that are integers. We can understand them kind of simply. T turns out, by some arguments about the incompressibility of these quantum Hall phases, just tells you the Hall conductivity, right? And that, of course, matches what we see in normal Landau level systems. And S is essentially the Bloch band filling index. It's telling you how much, if you were to remove a unit cell from the system, how much charge would you remove for the system? How much charge is glued to each unit cell of your periodic potential? Right? If you think about some tight binding model, that's just how many bands do you have filled? What's your Bloch band filling? So it's clear that if you don't have more than one band, then you're always going to have S equals 0, and that's basically your normal Landau level problem. And then your Hall conductivity will just be given by how many Chern bands you have filled by the arguments I told you before. So we can go through this data and start to try and classify all of the different gaps that we see, right? And right off the bat, we already know there's something that's beyond the non-interacting model because fractional quantum Hall states don't fall into this model. They have a fractional Hall conductivity that's not captured in the Hofstadter butterfly, and that's not surprising. Fractional quantum Hall is a correlated electron phenomenon, and the Hofstadter butterfly is simply a single particle quantum mechanics calculation. But okay, that's already known, but it already gives you sort of the example that we're ultimately going to look for. So then we can go through and we can draw lines for all of these integer and fractional quantum Hall states. We understand them. We can look at all of the lines that we have that follow integer T and integer S. That's basically what we expect from the Hofstadter model. We find there's a variety of them. These have been observed before, right? But then we can find some that don't fit into this paradigm, and there's actually 2 classes of those. One, which we'll call SBCI, have integer T, integer Hall conductance, but they have what apparently looks like fractional Bloch band filling. Okay? And then there's a set that have fractional Hall conductance and fractional Bloch band filling. And so the rest of this talk is basically devoted to trying to understand these 2 new things. Actually, this one is not so new. It wasn't given the same name and maybe not fully understood, but it was observed already in 2015 by Philip and Corey Dean. So anyway, we want to sort of understand how all this fits together. And so we can kind of go through and understand that, in fact, the integer quantum Hall and the Hofstadter type of gaps, even though interactions can play a role in the size of the gaps, various quantitative effects, they're basically single particle physics. Fractional quantum Hall effect, of course, is not, and neither are SBCI or FCI states because, again, they have some fractional quantum number, either in the Bloch band filling or the Hall conductivity. Okay, so what is the meaning of a fractional T or S? So if we go back to these definitions, fractional S is telling you that there's a fraction of a charge, fraction of an electron charge that's glued to each unit cell. So remove a unit cell, you're going to remove a fraction of a charge. Well, there's really 2 ways that can happen, right? One way is that you have a fractional charge in your system, right? In other words, you have some fractionalized state like a fractional quantum Hall state. But actually there's a simpler way, which is just that you're wrong about the size of the unit cell, right? Let's say your unit cell is actually, there's a spontaneous breaking of translation symmetry so that your unit cell is 2 or 3 times bigger, then removing one unit cell of the moire pattern only is going to remove a fraction of electron charge because you're not really removing a full translationally relevant unit cell of the electron system. And that's much simpler. That requires sort of less fancy physics, right, in order to explain. And that's why we end up terming things that have fractional S but no fractional T, symmetry broken Chern insulators, right? You can do it with a charge density wave. It basically is band theory with some sort of increased unit cell. But it turns out that fractional T, as originally pointed out by Laughlin, is a lot harder to get. To get fractional T, you really need to have a fractional charge in your system. And so fractional T is really telling you about topological order, right? So if you have fractional T, then you must have a fractional charge in your system. And so these FCI states, the states with both fractional T and fractional S, are something that's not a fractional quantum Hall state because that has 0 S, but it does have fractional charge. And so that's what we want to sort of try to understand. So how do we get a quantitative understanding of this? This looks like a total mess, right? We can change the electric field. This was actually done in a graphene bilayer for reasons that I won't get into. And these are very complicated data sets. So how do we even get a start? If we want to model this, if we want to understand the system, well, we do what we usually do is start with a single particle physics and make sure we can understand that. So our analytic approach is to ignore all of this relatively weak in comparison to the single particle physics, interacting physics, and say, let me take a plot like this and just focus on the gaps that are described within single particle Hofstadter model. And let me try to understand, to start with, what is that Hofstadter model? Can we model that? Is that something that we can actually get a quantitative handle on? So the way we do that is we look at, let's say, two integer gaps. If we pick a given field, we'll choose a couple of integer gaps. Let's say this one and this one. And we'll look at their slopes, and we'll look at their Bloch band fillings. And then we'll look at the difference between the two. So if you have a left gap and a right gap, you can basically calculate, what's happening is you're filling electrons as you move in that direction. And you're changing the Chern number, changing the Hall conductivity by T left minus T right, or T right minus T left. And that means that the Chern number of the band that you just filled is got to be that different. And the Bloch band index of the band you just filled has to be the difference between the Bloch band filling index of those two gaps. And so you can apply this analysis throughout this phase diagram and try to understand at the single particle level what are the Chern numbers of the different bands that you've got. Okay? Because then once you've got that, you can try to analyze those bands and understand what their many-body instabilities are, but you'd like to know what your single particle picture is before you start to turn on interactions theoretically. Okay? So to do that, we can, of course, apply that analysis to the data. We can also model our system and try to understand what we would expect. Okay? And it turns out that this is a system that we've spent a lot of time trying to understand. It's Bernal bilayer graphene. We have a pretty refined understanding of both the single particle physics and the many-body physics in the absence of a periodic potential. And we have a decent understanding of what the Moiré potential is. We know its wavelength, pretty trivially, right? And it seems like we should be able to model this from simply assuming it to be kind of a smooth, harmonic potential. One thing that we don't know is its exact strength, and another thing that we don't know is its exact phase. So we don't know, for example, if it's inversion symmetric or inversion antisymmetric or somewhere in between. So in order to try and understand this data, what we're going to do is we're going to take everything we know about bilayer graphene, which actually ultimately boils down to understanding that all of the physics is either happening in an n equals 0 orbital Landau level plus a periodic potential, or some slightly modified n equals 1 orbital plus a periodic potential. And then applying a periodic potential of unknown magnitude and sign and seeing whether we can get a quantitative match to the single particle physics.
So the graphenes are matched, but the boron nitride in the middle makes them wide.
No, so this particular device is a Bernal bilayer, so it's a graphene bilayer. On one side, it's got a boron nitride that is rotationally aligned to it that creates some 10 nanometer wavelength potential. Okay? And then on the other side, the boron nitride is not aligned. We can know this because we can put the electrons on the top, and there's no Hofstadter physics. You put it on the bottom, there's lots of Hofstadter physics, and we can tune that with electric field. So now we take the system and we try to understand based on the Landau, effectively we're in the limit where you have Landau levels and you're turning on a relatively weak periodic potential that doesn't mix the Landau levels very strongly, right? But it does make each Landau level broaden into kind of Hofstadter mini bands. And we can try to calculate as a function of the strength and phase of that moire what we expect, for example, along this cut, what we expect the Chern numbers of the bands to be. And then we can measure them. Here you see you start from nu equals 0, you end up at nu equals minus 1 and then plus 1. So that means you have to go from 1, or maybe it's minus 1 and then plus 2. So you have to go from 1 and then 3. And if you do that, what you find is that on this phase diagram of theta, and which is the phase and the strength of the moire, there's a very narrow region here shown in white where what you have to assume about the periodic potential in order to get a quantitative match to these Chern bands. Yes?
I'm just wondering, what do the edges of your system look like? So where does this moire potential end?
Okay, so it ends right at the edges of the so the way these devices are made, you put these things together, you attach some contacts which are graphite and effectively inert, and then you cut the whole thing where everything is smooth. So the edges are abrupt on the graphene lattice scale, modulo a bunch of disorder. This is quite complicating for transport experiments. It's not complicating for capacitance experiments because this is really an area average, and these devices are hundreds of square microns, and so any we've never been able to see any contribution that we could attribute to the edge. Transport's a nightmare, unless you do Corbino, in which case it looks the same as capacitance.
But you get the information.
Huh?
You don't get this information if you do Corbino, most of the details.
Well, this is not so different because all you're doing is looking at slopes.
Exactly
Yeah,
same as capacitance.
exactly. Yeah, and we do like to do that better, so we don't end up doing it. Yeah, Corbino doesn't really help you. It just tells you that it is indeed edges. It's nothing intrinsic about measuring the current through the sample. But
And typical size, you said, is a couple of microns? What is the typical size of your
area size, hundreds of square microns.
Oh, it's hundreds of
Yeah, like 10 by 10 or 20 by 20.
This is huge.
We make them big. Yes, we make them big. We make them big because that gives a signal for capacitance. That's just proportional to area. So we like to make them big. That helps, and they're extremely uniform. You know, the bigger they are, the better they are. Occasionally, we may see two domains of maybe the Moiré potential, which we can sort of.
But I mean,
But-
for a system that size, from Landau level broadening, you do not know the disorder? So I guess a theory is needed of some kind.
Yeah, you need a theory. You need some model. Yeah, which we don't have a good model. Yeah.
But cannot be hundreds of microns.
At zero field.
Zero figure.
I think it can be, yeah. Oh, well, I mean, the lateral dimensions might be only 10 microns. It's hundreds of square microns, but it may be 10 by 10. It's definitely more than 10 microns. Yeah. It may not be 100, but if it's 100, we're far from that. Yeah. Okay, so anyway, let me spare you the details, but we can go through and try and constrain this single particle model and generate what we think the single particle spectrum looks like, and find that in fact, we can get it to match pretty well. Now I'm color coding the Chern bands, the Chern numbers of the bands themselves that are separated by these gaps, and effectively this spectrum, it turns out, reproduces the single particle physics with a pretty high degree of fidelity. Let me just explain what I've done here, right? So this is our single particle Hofstadter spectrum as a function of the same thing that's on this axis, basically the flux, right? And that's the energy. And then I'm taking wherever there's a relatively large gap, I'm calling that a gap. I'm of course ignoring the very small gaps because I could do this arbitrarily finely and keep color coding Chern bands until I get bored. But I'm going to just cut that off somewhat arbitrarily for some gap size just to give an idea. It's going to turn out that's not very important anyway because it all gets mixed by interactions. And we find some sort of general features, that there are a bunch of rules that are followed. So Chern 2 bands always originate from something with the denominator 2. So this is a Chern 2 band that's it's narrow, close to half a flux quantum. Chern 5 bands are narrow, close to some rational fifth of a flux quantum, and so on and so forth. So there's some sort of counting rules which are just properties of the Hofstadter problem. And there are vastly different bandwidths available at fixed Chern number, right? And these are intrinsic bandwidths that come from the lattice. So for example, in this Chern 2 band, as you get close to half a flux quantum, the bandwidth gets very narrow, but then it broadens out as you get closer to, say, 2/3, right? And there are various splittings and so on and so forth. And that's important because basically it tells us that if we take our single particle picture, now we understand, we can say, all right, where do we see one of these interaction-driven states? Let's choose some value of the flux within the correct band, let's say the correct field, and then let's try to understand the many-body physics. Okay, so for example, we can take a Chern 3 band, right? This is close to 1/3 of a flux quantum. Here's what our data looks like. This is the Chern 3 band is basically between here and here, and we see two of these what we've termed symmetry-broken Chern insulator states in between, right? At 1/3 and 2/3 fillings of this Chern 3 band. Okay, we would guess, based on the arguments that I said before, that these should basically break the lattice symmetry, but not have any fractional charge associated with them. That would sort of be the Occam's razor argument just based on their quantum numbers. But now we can go and do some many-body calculation, right? So these were done by DMRG, by Mike Zalatel, who collaborated with us on all of these projects. And that's basically what's found for a very reasonable set of parameters, right? So you basically put in everything we know about, okay, we know the flux, we know the electron density, we have tight constraints on the strength of the moiré and the degree of Landau level mixing and so on and so forth. And what you find is that in fact the ground state from DMRG looks like what we sort of would have guessed. It breaks the lattice symmetry. Each of these gray dots is the center of a moiré unit cell, and you see that the actual unit cell of the device is considerably enlarged. Okay, good. And you can do this.
Are you actually using Coulomb interaction for this DMRG?
Yeah, this is a Coulomb interaction. That's right. Maybe it's Coulomb interaction screened by the appropriate gates.
It's
Yes.
not some model interaction.
No, it's not some model interaction. It's Coulomb interaction. Yeah. I think it helps that it gets cut off by the gate distance, et cetera. But it's relatively realistic. So anyway, as expected, right? Symmetry breaking, no topological order. Okay, another example. This is in a Chern -1 band. This is actually this Chern -1 band here that happens above half a flux quantum. You can see that you have, this is actually a Landau level down here, and you have fractional quantum Hall states. Then there's this Chern -1 band that's narrowing up there, and you again have what look a lot like fractional quantum Hall states. And indeed, if you then crank the DMRG, you find that you end up with a state that doesn't break lattice symmetry, but it does have fractional charge. If you go in the DMRG and you try to measure these quantum numbers, they match. You can do it, of course, numerically. You can vary something that's a little bit more annoying to vary in experiment, which is the strength of this Moiré potential. And you find that, in fact, what we'll call a fractional Chern insulator, FCI state, is pretty robust, right in the range. We think that this is, if we had guessed what the strength of the Moiré is based on literature relative to the strength of Coulomb, it's right in this pretty broad range between essentially freezing the electrons in a charge density wave or just having a compressible partially filled Chern band. Actually, if you look at this cut, you can see that, in fact, this looks a lot like what our normal fractional quantum Hall sequences look like, right? You have a third, it looks like you have a weak fifth, maybe you have a seventh, it's unclear, but it looks like you have a kind of conventional composite fermion sequence for partial filling of this Chern band. This is not at fixed, these are not at fixed Landau level filling factor, obviously, they're just at fixed filling factor within this Chern -1 band. So what numerics have told us so far is that, and as you could sort of guess by just looking at these things, they probably are basically Laughlin states. That's essentially the type of topological order that's realized. It's in a marginally different situation to a Landau level. It's in a Chern band. It has some finite bandwidth. But this is not so surprising. I mean, there's a certain class of theorists that have been surprised by the fact that there's finite bandwidth and you can still get a fractional Chern insulator. But I think anybody who's ever actually thought about physical systems, this is not too surprising. All Landau level systems have a finite bandwidth. There's always some disorder. You still get fractional quantum Hall. It's not that hard. So, it shouldn't be too shocking that intrinsic bandwidth doesn't automatically disqualify this from happening. But okay, it happens indeed in this Chern -1 band. I think one of the interesting things for which we don't have a good theory calculation at this point, it's somewhat more difficult to do this with multiple components, is that actually you can also see these fractional Chern states in higher Chern number Landau levels. In particular, this is a Chern 2 band, and you see states that have, again, this fractional Hall conductance at 1/6 and 1/3 filling of that Chern 2 band. In particular, this 1/6 filling state, which has a Hall conductivity of 1/3, is very similar to 1/3 filling of a Landau level in a two-component system. It has to break the lattice symmetry as well as have topological order, similar to the way a 1/3 spin polarized 1/3 Laughlin state has to break spin symmetry if there's in fact a spin symmetry in your system. And this 1/3 filling state, which is sort of 2/3 filling of this half of the Chern band, actually in principle doesn't have to break lattice symmetry. So that's kind of interesting because likely, especially given the hierarchy of how strong these states are, that's sort of a two-component type of state on this lattice, which is kind of interesting. So this has not been fully analyzed theoretically yet, but certainly just from looking at the quantum numbers, this 5/3, 1/6 state you can already see has to both have topological order and symmetry breaking because the Bloch band filling index is a 1/6. If we think the minimal charge in the system is a 1/3, then that means that you must have unit cell doubling, for example, right? So by the same arguments. Okay, so let me just wrap up in the last couple of minutes with some sort of outlook for what might be interesting, right? So for many years, there was a general idea that you'd like, how is it that you actually can engineer fractional quantum Hall states with interesting ground states? Well, in a Landau level system, you have relatively limited flexibility. You start with Landau levels. Landau levels have certain form factors, and that's basically what dictates the pseudopotentials, which then dictate the ground state. You can try to modify that. In gallium arsenide, you might make the well a finite width and try to take into account that. Landau level mixing changes that a little bit, but the range of knobs that you have is relatively small. There's a fair amount of tunability available in these systems just for changing what effectively those single particle form factors are, because now you have this lattice, and the lattice is giving your wave functions potentially a pretty rich type of structure. You pay a price sometimes of bandwidth, but not always. As I showed you here, this band is getting awfully narrow by the time you get close to half a flux quantum. So there's always somewhere in the phase diagram where you can do something interesting. So whether you can, for example, find nonabelian states, whether you can find something that's new, we don't know. That's something that I think numerics could be helpful with, but this is somewhat unexplored territory. There's a fair amount of knobs available here. Maybe something new will come out of it. Not clear. Obviously, twisted bilayer graphene is another. There's lots of ways to make moire patterns, right? Both with the boron nitride and with 2 sheets of graphene. That can give you more tunability. Again, there's a fair amount of different stuff you can do. There was an interesting proposal originally due to Meisam and Xiaoliang Qi that if you want to make a parafermion type of defect, but you don't want to use a superconductor, then if you have a fractional Chern insulator of the right type and you make a lattice defect of the right type, then you can localize some kind of parafermion defect. There's a few steps still missing here. You need to have the right type of 2-component fractional Chern insulator state on the right type of lattice with the right type of defect. But that's better than not having a fractional Chern insulator state at all. So that's sort of our first step towards this. How to understand this? I think that physically the real essential thing is to get experimental control over the lattice, right? The moire lattices are beautiful because they're very regular. They're kind of the analog of optical lattices in cold atom systems. You're taking advantage of quantum interference. It's pretty easy to make things the same wavelength if they're pretty stiff, whether it's laser beams or the intrinsic lattices. They're not going to be that much disorder in that lattice. If you now want to make single site modifications to that lattice and do that kind of microsurgery, you need to use a different approach, which is probably going to be somewhat less robust. But there's some ideas of how to do that. Certainly you can manipulate lithography on the appropriate length scale. So here's an example from a recent paper from Columbia where they can realize some non-interacting Hofstadter physics in a pretty dirty system with an artificial superlattice where it would be trivial to engineer defects. Whether we can do that and preserve the quality is a question. This is some numerics from Mike that suggests that in fact you can have, at least on a square lattice, there's a way to get a kind of equivalent of a 331 state that might be appropriate for this type of defect engineering. But that's work to be done. There's another final kind of interesting point here, which is in some ways kind of trivial, which is the fact that fractional quantum Hall states typically sit at 1 filling factor. If you want to have a transition between a 1/3 and a 2/3 fractional quantum Hall state, the only way you do that is by either changing the magnetic field at fixed density or changing the density at fixed field. And by doing that, you're going through a whole bunch of other fractional quantum Hall states. In principle, because the fractional Chern insulators, even though they have the same topological order as a fractional quantum Hall state, live on a different trajectory, then those trajectories can meet at a single point, right? So for example, here it almost happens. You have a fractional Chern insulator, and then you have a fractional quantum Hall state, and it almost looks like they intersect. They don't quite. One of them sort of peters out just before it hits the other one. But at various rational values of the flux, you should be able to induce, as a function, for example, of the strength of this periodic potential, a direct transition between, say, a 2/3 fractional Chern insulator and a 2/3 fractional quantum Hall state. And there's been a recent proposal, I don't have the citation here because it just came out on arXiv a couple of days ago, that at certain of these types of phase transitions, you realize quite exotic critical theories. There's some proposal that you get QED3 at one of these particular transitions or something that we might be able to realize. So what to measure, how exactly to get information out, there's sort of new types of phase transitions that in principle we can do, especially if we can get control over the strength of the lattice potential, which is actually not so terribly difficult to do, even without moving away from moires. So anyway, that's the talk. And I want to acknowledge in particular Eric Spanton, who really led this work. He's a postdoc in my group. He'll be on the job market next year. Sasha Zebrov, my first student, and Mike Zalatel, who really helped us understand all of this. So thank you for your time.